voids or interstitial spaces. The voids or interstitial spaces are of two types in the crystalline solids. The two types are octahedral voids and the second is tetrahedral voids. Now let us study each one of these one by one. Let us first take octahedral voids. Now octahedral voids, we need to know first, they are the voids formed by 6 particles arranged in octahedral shape. So that therefore the coordination number of particle in such voids, whenever a particle gets trapped in these voids, will be in contact with the 6 particles which are forming these voids. So therefore the coordination number of particles in such voids will be what? Will be 6. Then you need to know the location. The location of these particles in FCC unit cell is all edge centers plus body center. Therefore, if we can make out, we know, I will show it to you by diagram also, each edge center particles 1/4 portion lies in one unit cell. So it will be 1/4 of the particles which are lying at the center of edge and the whole particle which is at the body center. So and how many edges a cuboidal is having? 12. So 1/4 of 12 plus 1, it makes it 4, which is also the number of particles per unit cell. So remember, the location of the octahedral voids in FCC unit cell is all edge centers plus body center. And therefore, how many octahedral voids we have? 4 in case of FCC. From here we can make out that what is the number of units octahedral voids we have. Always remember the number of octahedral voids per unit cell is always equal to Z. It's the number of particles per unit cell. It means what? Therefore, in case of SCC, BCC and FCC, since Z is 1, Z is 2 and the Z is 4, we can easily make out that the octa voids are how many? 1, 2 and 4. So this is the number of voids we have in these unit cells. Then you need to know the size of octahedral voids. Octahedral voids are the one which are lying at the center of these 4 particles. So basically it is this triangle we can draw. If this is R, this is R and this is small r, we can draw up, this is at an angle at 90 degree. Using a simple Pythagoras theorem, we can find out the relationship between small r and capital R, and it is found to be that this size of the octahedral void, which is indicated by small r, is equal to 0.414 times of capital R, or it is 41.4% of the capital R. That means it is 41.4% of the size of the particles which are forming these this crystalline solid. Now let us first draw an FCC unit cell. This is one FCC unit cell. You can make out the corner particles and the particles which are lying at the center of each face. This is one FCC unit cell. Now, each edge center, this one is a location of an octahedral void. So this is how we can have 12 edge centers and the body center also. Let me show you how this edge center is an octahedral void. Definitely, if this is one unit cell, we will be having another unit cell at the top, which will be having this particle, suppose, at the center of it, center face, and similarly, we will be having one particle here, which is actually at the center of the face, which is lying on this side. So you can make out this particle, this black colored particle is in the center of this 4 particles, which will be in contact with this particle which is lying at this. This forms one square pyramidal, and this is another one, this center one. This is another pyramidal we can have. So this, in this way, this center particle will be in contact with 1, 2, 3, 4, 5, 6. So these are 6 which makes it what octahedral void. Similarly, each center like I can make out this is your square, and this is the top one which is there. So this is what square, pyramidal, that makes it square bipyramidal, and we know the other name of the octahedral shape, it's called square bipyramidal. So this is how these are the locations of the octahedral void in an FCC unit cell, and now you know everything about these voids. Let us move to the tetrahedral voids. Tetrahedral voids. As the name suggests, these are the voids formed by 4 particles arranged in tetrahedral shape. Therefore, the coordination number of a particle in these voids will be 4, because once a particle gets trapped in these voids, it will be in contact with the 4 particles which are forming these voids, so therefore its coordination number will be 4. It is almost as like this, if we can make out. This is, so if these are the 4 particles which are making it, anything which gets trapped between them like here will be in contact with these 4 particles. So that's how we can make out this is octahedral. Then the question comes is, what exactly is the location? So location of these voids in FCC unit cell. The location is 2 on each body diagonal. So 2 on each body diagonal will give you the number of tetrahedral voids in the FCC unit cell. So now we can make out, let us do the calculation part. We know if there are 2 tetrahedral voids on each body diagonal, then the number of tetra voids in FCC will be 2 into 4, because each cuboidal has 4 body diagonal, so it is 8. So this suggests that the number of tetrahedral voids per unit cell is always equal to twice of Z, because we know in case of FCC the Z is 4, so and it's double of this, so it's 8. Therefore, we can make out in case of SCC, BCC, FCC, since Z is 1, Z is 2 and Z is 4, the tetrahedral voids will be 2, 4 and 8. This is how they will be arranged in this. And now we know the location. Let us find out their size. Now the size of tetravoids, which we represent by small r. We know actually it will be how it is related to capital R. Remember, this small r is 0.225 times of the capital R. The capital R is the radius of the particles which are forming the unit cell or the crystalline solid, and small r is the radius of the void. So it is 22.5 times of the capital R. And let us see now from the diagram of the FCC unit cell that how they can be shown in an FCC unit cell. Let us see now the location of the tetrahedral voids in an FCC unit cell. This is what we have, an FCC unit cell. Now this is how the corner particles and the we have a particles at the center of each face. Now as I have told you, each body diagonal has two tetrahedral voids. So if we know that we have divided this unit cell into 8 parts. This is one unit cell which has been divided into 8 parts. Let us now take out this unit cell and let us draw this outside. It will come out to be like this. In this, the particles are here, here, here and here. Now you can easily make out, if we have a particle at the center of this, it will be in contact with all these 4, and that means what? The center of each, center of this 1/8 of this part is basically a location of a tetrahedral void, because a particle is here like this, here it is here, it will be in contact with 4 such particles like this, and it will be forming a tetrahedral, and it is arranged in a tetrahedral shape. Now if we can join this end to this end, we can easily make out that this particle is lying at the what? Body diagonal. And similarly this same type of particle will be there at this point, which is there on the other side of this 1/8 part. So that means what? This body diagonal is having how many tetrahedral voids? 2. Similarly, all the 4 body diagonals will be having 2 tetrahedral voids. So then total the FCC is having 8 tetrahedral voids. Now the most important thing, it means what? That if we divide one FCC unit cell into 8 parts, the center of each part through which a body diagonal crosses is basically a location of a tetrahedral void. So this is how we can now make out what exactly the voids are and the types of the void which are available.